So in the previous lecture, we introduced compactness, and we saw that the interval 0, 1, the closed interval 0, 1 is compact. So just as in the case of connectedness, we can ask what happens for products or subspaces. So if X is compact, so what is compactness? Behave with taking products or taking subspaces, right? Okay, so exactly as in the connected case, so if X is connected and Y is a subspace, then Y need not be connected. Right? For instance, we can take X equal to R and Y we can just take just 2 points, 0 and 1. Yeah. So clearly Y is just the union of these 2 points. Yeah. So clearly Y is not connected. And in the same way, so if X is compact and Y contained in X is a subspace, then Y need not be compact. Right? So we can take X equal to 0, 1 and Y equal to the open interval 0, 1. Okay. So there is a homeomorphism from R to 0, 1, right? And we saw that R is not compact. Yeah. Thus, the open interval 0, 1, since homeomorphism obviously is going to preserve compactness. Yeah. So, and we saw that R is not compact. Yeah. We explicitly wrote down an open cover which does not have a finite subcover is not compact. Yeah. What this homeomorphism is left as an exercise. Okay. So let's come to products, and that is as in connectedness, if X and Y are connected topological spaces, we saw that their product is connected. So in the same way, we will prove that if X and Y are compact topological spaces, then their product is also compact. Yeah. So the crucial ingredient for that we need is this lemma, which is called the tube lemma. So let Y be a compact topological space. Let X be any topological space. Okay. Let W contained in X cross Y. So X cross Y is obviously always, given the product topology, be an open set containing this X cross Y. Yeah. So then there is an open set U contained in X such that X is in U and u cross y is contained in W. Okay. So, let us make a picture of this lemma and explain what it is saying and why it is called a tube lemma. So, this is our x and this is our y is compact, right, and here we have this is x cross y, yeah, and we have this open set W, W is some open set which contains x cross y. Then what this lemma says is there is a small neighborhood u around x such that this entire disk around x cross y is contained inside W. It contains this entire tube. W contains, so this region is W and this is u cross y. Okay. So, let us see how to prove this lemma. Proof. So, given any point y in y, there is a basic open set so given any point in y, so we have the point x comma y which is in x cross y which is contained inside W, right, and W is open in the product topology, which implies that there exists open sets uy contained in x and vy contained in y such that this x comma y, this is in uy cross vy and this is completely contained inside W. Yeah. So, we are taking any point over here, this point is x comma y, so we are just saying that there is this open neighborhood. So, this is uy and this is vy. So, uy cross vy is contained in W. Okay. So, clearly, and this happens for every y. Right. So, thus we can write y as a union of y in y, v sub y. Okay. So, since y is compact, this has a finite subcover. So, we can write y as j equal to 1 to n v yj. We can write this as a finite union, right? Okay. So, let u be equal to intersection of the u yj's. So, note that each of these u yj's, it contains x, right. So, therefore, u contains x. Each of these u yj's is an open set containing x. We are taking a finite intersection. So, therefore, u is an open set such that an open set of x containing an open set in x containing the point x. Okay, so then u cross v y I is contained in u y I cross v y I, which is contained in w. And this happens for all I, so this implies that union I equal to 1 to n u cross v y I is contained in w, but this union is simply u cross union I equal to 1 to n v y I, this is contained in w, but the union of the v I I is simply y. Is contained. Okay, so this completes the proof of the lemma. Okay, so using this lemma, which is the crucial ingredient, let us prove the theorem, our next theorem. Let x and y be compact topological spaces. Then the product x times y is compact. Okay, so let's prove this. Suppose we are given an open cover B, an open cover. Okay, so then fix an x in x. Yeah. So then we have x cross y, which is contained in x cross y, right? So as x cross y, so note that, consider the map. Consider the map y to x cross y, which sends y to x comma y, right? So this map is bijection, factors through x cross y, and this has this subspace topology. Right? So it is easy to check. So the map from y to x cross y is obviously continuous because the image of y, so let's call this f, let's call this f sub 0, let's call this I, yeah, that f sub 0 is a homeomorphism. Okay, yeah, so this shows that x cross y is compact, right? And now, so we can write x cross y is equal to union I in I intersected wi, right? And since x cross y is compact, this implies that this has a finite subcover right, which implies that this x cross y is actually contained in some finite set wij. Okay. So by the previous lemma, so let's this finite subcover, let's write this as union I sub x contained in I, or rather I in I sub x I wi. Yeah. So x cross y is contained in some finite subcover. We just collect the indices in that subcover and put it into the set I sub x. Yeah. So here is a finite set. Okay. So now by the previous lemma, there is an open neighborhood u sub x of x in x such that, so what did the previous lemma say? So let's look at the previous lemma. So y is compact, and if x cross y is contained in W, then there is a small neighborhood u of x such that u cross y is also contained in W. So we will use that. Yeah. Such that u sub x cross y is contained in union Wi. Okay. Now this can be done for every x in x, right? So thus, when we do this, we get an open cover of x, u sub x. Now again, as x is compact, this has a finite subcover. So we can write x as u x sub j. Okay. Yeah. So then x is equal to, x cross y union u sub x xj cross y which is contained in j is going from 1 to n. Each of these is contained in this indexing set Wi, right? And now the index set is finite, yeah? So each I sub xj is a finite set, subset of I. This implies, so let me just, this is equal to union I in 1 to n Wi. This index set is finite, right? So thus x cross y, so thus we have found a finite subcover. A finite subcover for x cross y, right? So this subcover is finite because this index set over here, that's a finite index set. So this completes the proof of the theorem. Right. So as a corollary of this, we see that the closed interval 0, 1, I mean when we take product of it n times, is compact. Okay. So next let's make some observations about compactness. So proposition, a closed subspace of a compact space is compact. Okay, so let's prove this. So let y contained in X be closed, and suppose that X is compact. Right. So our aim is to show that y is compact. So we will what we have to show is, given any open cover for y, it has a finite subcover. So given any open cover for y, we will construct an open cover for X, and from that we will deduce that y is compact. So let y be equal to union I in I, Wi be an open cover for y. Right. So since y has a subspace topology, so thus there exists Ui contained in X open such that each Wi is equal to y intersection Ui. Right. So this implies that y is contained in Ui. Y is contained in this collection of open sets. This is open in X. Right. So suppose this is our X, and let's say this is our Y. So first we are given an open cover for Y. Right. This we extend to an open cover for X. I'm sorry. We cover this like this. We find open subsets. We find a collection of open subsets in X such that their union contains Y. Right. And now, since Y is closed, we may write closed in X. We have X minus Y is open in X. Right. So this region is open. Right. So we can write, we may write X as X minus Y, disjoint union Y, but this contained in X minus Y union Ui. Right. Yeah. So this is open in X, and each of these is open in X. Right. So X is contained in this, and all these are of course contained in X. So this implies that we have gotten an open cover for X. Yeah. Since X is compact, this has a finite subcover. So let's say the finite subcover looks like this. Right. I mean, this may or may not be present, but there's no harm in throwing it in, throwing an extra open subset into it. So now intersecting both sides with Y, we get y is equal to, this is this is empty, y intersected with x minus y is empty. We simply get this is equal to wij. Yeah. So thus the open cover we started with has a finite subcover. Okay. So this proves that y is compact. So we will end this lecture here, and in the next lecture we shall show that a closed subspace of Rn is compact if and only if it is closed and bounded.